Having realized that what we need to do is common calculations like going from a function like x squared and finding its antiderivative so that we can use the fundamental theorem of calculus, we're going to look for some general rules. Well, if x squared, when we antidifferentiate, it goes to x cubed over 3, we can generalize that to x to the n. If we were antidifferentiating it, we'd get one higher power and divide by the new power. So we're going to be finding the opposite rules of our derivative rules. Add 1 to the power here and divide by the new power. Now those properties we saw earlier are going to come into play. What would the antiderivative of x squared plus 3x minus 2 be? Give that a try yourself, and in a second we'll go through it. Okay, if we have a sum of terms, not a product but a sum, we can antidifferentiate each one individually, and we just said that this would be x cubed over 3. 3x to the 1 would give us, doesn't matter if we have a multiplier out front, we'll keep it around, we'll get x to the 1 higher power divided by the new power, minus 2, and that's like x to the 0, we'll get x to the 1 over 1. Or the area under a constant. It's easier to think of the rules. Oh, and I just forgot here, I just realized, we should always have a plus c, and we should definitely have had a plus c up top with the power of x here. So polynomials have fairly straightforward antiderivatives where we just take term by term, add 1 to the power, and divide by the new power, and then don't forget the plus c at the end. Let's try some trig functions. What would I have to differentiate? That's what you have to think. What would I differentiate to get cos of x? I think we all agree it's sine of x, and the question is just plus or minus. Well, just remember, the derivative of sine is cos, so the antiderivative of cos is positive sine. Antideriv. When we get to sine of x, here it'll be cos of x, but, I won't put the line there. If I differentiate cos, I don't get sine, I get negative sine, so I'll need a negative out front here, and can't forget plus c plus c. So just to check this, the derivative, we're saying that when I differentiate this, I should get sine. Well, I think we do, because we're going to get negative times the derivative of cos of x, which is negative sine of x plus 0 equals positive sine of x. So when we differentiate this, we get sine. So when we anti-differentiate sine, we get this. And then, of course, we can combine things by sums very easily. Our power rule, add 1 to the power, divide by the new power, and the antiderivative of sine is negative cos, and we can throw one constant for the whole thing at the end there. Last but not least, let's do some more traditional ones. Just think when we differentiate, what do we have to differentiate to get e to the x? This is the easiest one, and it's just e to the x. What about 2 to the x? Again, it'll be something like a power, but remember when you differentiate 2 to the x, hopefully you do remember, you get 2 to the x times ln of 2. Because the base isn't the nice natural exponential base, we get a ln of the base as a multiplier. If it had been ln of e, it would just be 1, but it's ln of 2. And so if I said my antiderivative was also 2 to the x, that would be wrong. Because I differentiate 2 to the x, I get something extra that I don't want. There's no ln of 2 out front. Fortunately, it's easy to fix, because ln of 2 is just a constant. If we put a 1 over ln 2 times this, we'll get the same derivative over ln 2. These will cancel, and we'll get back to our 2 to the x. So 2 to the x over ln of 2 is the antiderivative of 2 to the x. These last ones here are mostly recognition. 1 over 1 minus x squared all square rooted. That should sound an awful lot like arcsine. When we differentiate arcsine, that's exactly what we get. And likewise, what do we differentiate to get 1 over 1 plus x squared? It's arctan of x. Last but not least, what do we differentiate to get 1 over x? We differentiate ln of x. We'll actually return to this one a couple times. Turns out there's a little subtlety to this. We'll come back to it after the next example.